So my name is Luana Ruiz. I'm a postdoctoral fellow here at MIT CSEL with the METEOR program. My mentor here is Professor Stephanie Egelka, and my research focuses on machine learning on large-scale graphs, and particularly graph neural network architectures. Graph neural networks are these machine learning architectures for problems on graphs or networks. So to give you a concrete example, one problem that you might have on a network is, say that you have a company that sells products and these products have certain similarities. You can use a graph to model these product similarities, where each vertex of the graph can be seen as a product and the edges can be seen as product similarities. And say now that your user base has given you some ratings to some of these products. So some of the nodes in this graph have ratings associated with them. A graph neural network is a machine learning model that you could use to, using these ratings that a user has given to some of these products, predict the ratings that this user would give to other products in the network. And these ratings can then be used to do product recommendations, like targeted product recommendations to this user. The key property here that I was studying or trying to understand in graph neural networks is something that we call transferability. So by transferability, what I mean is that you're able to take a graph neural network, one of these models, train it on a smaller graph, which is less costly than training it on a large graph, and then transfer this learned model to a large graph with performance guarantees, so without making many mistakes. And why do we care about doing that? Well, because in practice, most real-world networks, for instance, the product similarity network I described in recommendation systems, they can have millions or billions of nodes, and so they're very large. It's infeasible to try to train these models on these large networks. And so if we can then sample a few nodes from them, train our model, and transfer it with performance guarantees, then we're saving a lot of computational and time and complexity. I believe that the main challenge is, when you come from an engineering or a computer science background, you, depending on your area, and this was my case, you have more of an applied background, so you work more in application. And so for me to be able to understand these theoretical properties of graph neural networks, I had to take a deep dive into the theory and understand some concepts from mathematics that I hadn't been exposed to beforehand. So that was the biggest challenge, I believe. So I'm really excited about the fact that I am in a very interdisciplinary field. So I have an electrical engineering background. I am now in more of a computer science, artificial intelligence department. And so I'm really excited about all the collaborations that can, happen at the intersection of these two areas, and that I've already started working on with Professor Stephanie. And I guess something that I wanted to say is I'm very thankful for the support of the METEOR program and also the sponsors, because they have been incredibly generous with the opportunity to both visit here before starting my postdoc, which is a little bit shorter, and also by supporting me, by going to conferences and meeting people, and which kind of all helps in these goals that I have for my career.